So this is a quantum information theory talk, and it's joint work with these friendly people here, Sergey, Bravyi, Yash, Sharma, and Mario Szegedy. Now let me start with a bit of motivation. The motivation is sort of quantum networks, or if you want to be really grand, quantum internet. So the idea is that that we have some sort of quantum network. Ideally, there would be like n parties, and they would be connected by pairwise quantum channels, and then, of course, they can just send each other qubits at will. Right, and if you have such a network, there's lots of interesting things you can do. You can do quantum key distribution for the purposes of cryptography. You can reduce communication complexity, sometimes exponentially so. You can combine n little quantum computers into one big quantum computer by sort of letting them communicate amongst each other when they need to do a gate operating on one qubit from party 1 and one qubit from party 2. But the setting I want to talk about here is a setting where they actually don't have quantum channels between them, but only classical channels. So they can communicate with each other over, let's say, I don't know what, let's say a phone channel or some radio channel or whatever, classical bits only. Right, and at that point the whole thing falls apart because there's really nothing quantum you can do in that case between the parties, unless of course they share already at the start, they share some entangled state, some n-party entangled state. Right, so in particular it's still okay to have only classical channels if the parties actually share EPR pairs amongst each other, because, you know, if I share an EPR pair with David and we have a classical channel between us, I can actually send him a qubit by teleportation. Right? And this, of course, is very well known, nothing special here. So then the question is, like, what kind of shared n-party entangled state are we going to give to these parties? Right now, if we want to be sure that every pair of parties has sort of an EPR pair between them so that they can actually teleport, that's a lot of EPR pairs. Right? Here you can see a picture. Let's say you have 4 parties. Then every party needs to be involved in 3 EPR pairs, like one with one EPR pair with each of the other 3 parties. So in general, let's say if you have n parties, that would be n choose 2 EPR pairs, and every party would have to hold n-1 qubits. Right? This certainly guarantees that there's sort of one EPR pair available between any pair of parties. But it's kind of expensive in terms of how big the state is that's being shared. n-1 qubits per party, that's kind of a lot. You can do something slightly smarter. You could do a star graph where there's sort of one party in the middle who is like sort of the relay center, and this one party shares EPR pairs with all the other n-1 parties. This is actually enough for any pairwise communication because of entanglement swapping. If you have, let's use a bit of chalk. If you have, let's say, something like this, right? So this would be the person in the middle. And these 2 parties, A and B, want to have an EPR pair between them. They don't have one initially because there would be an EPR pair between the center in A and the center in B. But there's a simple protocol using classical communication and local quantum measurement, LOCC protocol called entanglement swapping, that would actually sort of, by the actions of this person in the middle, would establish an EPR pair directly between A and B. And at that point, those 2 parties can teleport. The downside of this thing is that the person in the middle still has to hold a tremendously large state. The person in the middle is doing basically all the work and has to hold an n-1 qubit state. And we are sort of motivated by the situation of a lot of very small quantum computers, so none of these parties should hold very many qubits. So we want few qubits per party. Even for the party holding the most qubits, it shouldn't be a lot. It certainly shouldn't be linear in n. And we're going to make an extra assumption, like, you know, having EPR pairs all over the place is probably too much. So let's say that we know in advance that there will be only k pairs of parties out of these n that will want to communicate, so that will want to have an EPR pair between them for teleportation. But we don't know in advance which k pairs of parties this would be. And now the goal would be to sort of give them in advance one big n-party resource state. Actually, it shouldn't be very big, that's the whole point. Such that after we learn, okay, parties 1 and 5 need an EPR pair, parties 2 and 7 need an EPR pair, etc. After we get a specification of k pairs, somehow we should be able with LOCC to convert this initial resource state into those k specified EPR pairs. And we want to do that as efficiently as possible in terms of the number of qubits per party. Right, so this is basically what I said. So For a given integer n, that will be the number of parties in our network. For a given m, that will be an upper bound on the number of qubits per party. And for a given k, the question is there an n-party resource state psi with at most m qubits per party, such that for every partial matching that sort of pairs up k pairs among the n parties, there is an LOCC protocol that takes the fixed resource state psi and converts it into EPR pairs between those k specified pairs. And the setup is that all the n parties learn in matching m, so everybody knows sort of who needs to be connected by EPR pairs at the end. And the same resource state psi has to work for each m, right? So the resource state psi is fixed at the start, and only then do you learn, okay, these different pairs of parties need to end up with an EPR pair. So this is the question we're studying. I think it's a new quantum information theoretic problem, and we have positive and negative results. And let me just say what are sort of the extremes of what we're striving for. The biggest k that you could hope for would be n over 2. This will be the situation of a perfect matching. Think of n as even, right? Then k being n over 2 means that like you're sort of like everyone is sort of matched up with somebody else, and there will be n over 2 pairs that should end up with EPR pairs at the end. And we want m, of course, to be as small as possible, ideally only 1. Right? So ideally, every party in this n-party state should hold only 1 qubit. That's the best achievable. And these are sort of two extremes of a trade-off. And what we present is, first of all, some positive results on this trade-off, 3 of them. So we show that there is a resource state, psi, that achieves this up to the maximal k, so this is as good as it gets, and it only uses log n qubits per party. So this is already a lot better than this idea where you sort of connect everybody by EPR pairs, because then at least one party would have to have n qubits. We now ensure that log n qubits, even for the party with the biggest computer, is enough. Now, we would like to reduce this further, so we have 2 results where m is a constant. So first we have a result where m is only 10 qubits per party. And now we can't go up to the biggest possible k, like n over 2 is not achievable, but we can make k as big as n over polylog n, which sort of is not too bad compared to the maximal n over 2. And then last but not least, the other extreme would be m equal to 1, and we also have a result there. So there exist resource states where every party just holds 1 qubit, and you can connect up to log n pairs with an EPR pair. Right, and you can sort of, like somebody told me I should draw a graph, but I don't really know how to do that, so let me just sort of make a picture. This is some trade-off between the best achievable k and m. And these are all upper bounds, these are all positive results, and we also have a negative result, which in some cases is tight. So we have this proof that that the number m, the number of qubits per party, is lower bounded by this complicated looking expression here. Let me instantiate this in 2 cases. So first of all, if you want m to be constant, order 1, so that's corresponding to construction 2 in particular, then k cannot be equal to n over 2. In fact, it's sort of upper bounded by n over log n. And in particular, that means that this result here is essentially tied up to the power of the polylog. Right, so this c that we have here, I don't know, maybe it's 4 or 5 or something. In the lower bound it would be 1. But n over polylog is the correct answer here if you want the parties to only hold a constant number of qubits each. And another extremal case is when you want k to be as big as possible, so you plug k equal to n over 2 in here. And what follows is that m cannot be constant. It needs to be at least log n. Now that's not very impressive because it's like an exponential off from our upper bound here. We have an upper bound for k equals to n over 2 where each party has log n qubits, and we prove that they need at least log n qubits. And this is like an embarrassingly large gap between our upper and our lower bounds, but I don't know how to improve it. Right, so this is basically a summary of the main things that we do. And now let me sketch first the constructions and then have one slide about the obstructions, the lower bound. So constructions 1 and 2 are relatively straightforward. Effectively, what you do here is you choose sort of a well-connected graph with n vertices, and you put 1 or more EPR pairs on the edges of this graph. And this is a fairly intuitive thing, but you need to find the right graphs to get efficient constructions where each party holds only a few qubits. So suppose you have a graph, right? Here's a simple example of a graph. You can again do entanglement swapping. If you have a graph and you want to connect let's say parties A and B with an EPR pair, and they don't directly share an EPR pair already because there's not an edge between them, but there is a path between them, you can just do entanglement swapping along the path with LOCC so that at the end of the day, A and B share an EPR pair. Right, so this should be pretty intuitive. But if you now want to connect many different parts simultaneously, k of them, you run into trouble. Because it could be that, let's say your graph is connected and you have two different pairs of parties, A1, B1 and A2, B2. Let me draw it like this. So this would be A1 and B1. There's a path between them, so by entanglement swapping you can connect them with an EPR pair. But it could be that another pair that you want to connect, that the path between A2 and B2 goes through the same edge. Right? Now, if there's only one EPR pair on this edge, you can't sort of do the entanglement swapping twice. So this runs into trouble with sort of if different paths share edges, so we have to do something about that. The issue is you can't use the same EPR pair twice in this construction. So we need good graphs here, and the first graph actually completely avoids the problem. So this is a construction by Yuri, Mezei, and Mesarosh. And they show that there exists a graph G, n-vertex graph, where the degree is only log n, order log n, so every party has like log n neighbors. And for every perfect matching, so for every way to pair up the n vertices sort of in n over 2 disjoint pairs, there will actually exist n over 2 edge disjoint paths connecting those n over 2 pairs. And this completely avoids the problem that I drew on the board. It just doesn't happen because there will always be paths that do not share edges, and therefore you don't have to use the same EPR pair twice for your entanglement swap. Right, so you can convert this into a resource state by just putting one EPR pair on every edge. So how many qubits does every party have? Well, they share an EPR pair with all of their neighbors, but they only have order log n neighbors, so every party holds only order log n qubits. And to create the n over 2 pairs after the perfect matching has been given to you classically, or rather to the whole network, everybody should know these pairs. At that point, you can do entanglement swapping along the n over 2 edge disjoint paths, right? And you don't bump into the problem that you have to use the same EPR pair twice. But this does not use, so this would be construction 1. And it has an m, which is not constant, and we want to push down the m as much as possible. And for that, we use a different class of graphs. So for construction number 2, the idea is the same, but we use a different class of graphs. And this is by combining a result from Bolebash and Broder, Vries, and Upval. So they showed that there exists a family of graphs that are 5 regular, so every party just has 5 neighbors. And up to a k n over polylog, if you sort of have n over polylog different disjoint pairs, there will be sort of paths that connect these pairs. And they will not be edge disjoint, but they will be almost edge disjoint, in the sense that every edge will occur on at most 2 of these paths. And it should be kind of clear like how to create a resource state now. I mean, there's a little bit of latency here in the sense that edges are sometimes used twice. So we just put 2 EPR pairs on every edge, and you get construction number 2. Right, and how many qubits per party do we have? Well, every party has 5 neighbors. If there would be 1 EPR pair shared with every neighbor, that would be 5 qubits per party. But we actually need 2 EPR pairs per edge, so that's 10 qubits per party. Right, and that's construction number 2. And really, sort of the hard math was already done for us by all these people here. It's just sort of a matter of realizing that you can use these nice expander-like graphs to set up such a resource state, just using EPR pairs. Now, our third construction, this is something quite different, and I would say a lot more complicated. And this is for the extremal situation where you just want the parties to hold 1 qubit in total, right? That's really sort of rock bottom. Clearly, this whole problem becomes unsolvable if they have 0 qubits, right? So this is really one extreme of the trade-off. And this is super restrictive, and you might ask yourself, like, if this is even possible, even for k equals 1. Right, in the case of k equals 1, what that means is that somebody tells you one particular pair of parties, A, B, and only those need to end up with an EPR pair. And in this case, and I'm sure most of you have seen this before, in this case it is realizable. There is a resource state, an n-party, n-qubit resource state that realizes this, and it is the GHZ state. Right? So this is a well-known trick. If I give you the GHZ state, this is just 1 qubit per party, there is an LOCC protocol that will sort of create an EPR pair between parties A and B for any A and B. And the way it works is just that the other n-2 parties, they measure their qubits in the Hadamard basis, and they communicate the outcome. And sort of, I guess, the XOR of these n-2 bits, they tell what kind of Pauli correction, let's say, Bob needs to do to end up with an EPR pair with Alice. So at least for k equals 1, this setting is realizable. There exists a solution to our problem for k equals 1. Sorry, for m equals 1 and for k as large as it can be. But we want to bump this up further. We want to do this for a much bigger k. And you can't just sort of repeat this construction, because then, you know, if you do, let's say, 10, if you give people 10 copies of this state, everybody holds 10 qubits instead of 1. So somehow we have to cram multiple things into 1 qubit per party. And the way you can do it is by putting a so-called Reed-Muller error-correcting codes in superposition. So you can think of the Reed-Muller code as, so the code words correspond to functions, in fact low-degree polynomials, that map L bits to 1 bit, and n, the number of parties, is going to be 2 to the L. So these are strings of n bits, and the superposition of strings of n bits is just an n-qubit resource states with 1 qubit per party. And it turns out that this is actually, this satisfies our definition for k roughly log n. I think 1/2 log n actually. And there's a very technical proof, which is all due to Sergey Bravyi, like all credit to him. Very technical proof, which shows that you can partition, so I specify k pairs to you. That means there's n-2 k parties that do not need to end up part of EPR pairs. And those parties you can somehow partition into a group of parties that should measure in the x basis and another group of parties that should measure in the z basis. So they do those measurements, they communicate their outcomes to the 2k parties that should end up with an EPR pair. And this then tells the other parties what Pauli corrections to do. This whole construction is in the stabilizer formalism. So what you do is that sort of at the end of the day, you end up with sort of a stabilizer description of k EPR pairs between the right pairs of parties. And this is a really annoyingly complicated induction. I don't have much of a feeling for it. Sorry? Yeah, I'm getting close to the end already. Okay, so this was our construction number 3, very different, much more complicated than constructions 1 and 2. Now let me spend one slide on the lower bounds. So here's a repetition of the lower bounds. So this puts some constraints on how many qubits every party needs to hold if you want to go up to a certain k. And the proof is by a subtle dimension counting argument. So the idea is the following. So suppose somebody, this is for the, I'm going to sketch it here for this special case where k is as big as possible. So where you're given a perfect matching of the n parties into n/2 disjoint pairs. So suppose somebody gives us such a pairing, then let ket pi be the final state we should end up with, which consists of n/2 EPR pairs between sort of the specified pairs. Right, and that means that from our fixed resource state, LOCC should somehow be able to create all of these pies. From one state, LOCC should be able to create all of these pies. That's a requirement. And we're going to now consider a subspace which will be the span of all of these ket pies, and then a bunch of copies of them, R. R is going to be about log n. So we're looking at the space that is spanned by all of the ket pi states, tensor R. So these are states of R times n many qubits, and we take the span. This is some subspace. And then we prove upper and lower bounds on the dimension of this subspace, which combined gives us the lower bound. So here's the lower bound. So this involves some combinatorics, some graphs, counting permutations, and similarly for claim 2. And claim 2, this is the only part where the existence of good LOCC protocols is actually used, and where the existence of a good resource state psi is used. So in the proof of claim number 2, which is an upper bound on this dimension, we consider the set of states sort of the largest possible set of states that LOCC can produce from one fixed initial n-qubit resource state psi. Right, and I'm not going to prove these two claims, but if you put them together, you get the lower bound m over log n. And you can do this proof in more general case when k is smaller than n over 2, and you get this more complicated expression out of it. So I hope this gives a little bit of a flavor of this lower bound. So that's basically the end. So this is the question we asked. Is there an n-party resource state psi with at most 1 qubits per party, such that for every specified k pairs of parties, there is an LOCC protocol that gives those parties an EPR pair? Right, and the motivation is once these parties have an EPR pair, over classical channels they can actually exchange a qubit. Here are our results, sort of going from largest m to the smallest possible m. Here's our lower bound. A few open questions before David really stops me. Better constructions, of course. This is not tight, especially case number 1 doesn't match our lower bound at all. Can we go beyond stabilizer states? Everything we do is in terms of stabilizer states, including this rather complicated third construction. This one I mentioned already. This is kind of embarrassingly big gap between upper and lower bounds. Can we improve this? Log n would be optimal. I'm kind of conjecturing that's the right answer, but who knows? And what if we allow small errors in the k output pairs, right? If you want to make this stuff sort of more realistic, you have to consider noise in your network. And there the situation is not great because there's a recent paper by Contreras, Tejada, Palazuelos, and de Vicente, and they show that if you have constructions where your EPR pairs are a little bit noisy, let's say a small constant amount of noise per EPR pair, then this basically destroys everything, at least for constructions 1 and 2. If you have these constructions with EPR pairs on edges of graphs, like noise is going to break it.
I think destroys everything is a good point to end on.
Yep.
Thank you, Ron.
Yep.
Thanks for the nice talk. I had a question about these constructions 1 and 2. So you kind of needed to find, at least the way these graph theoretic results were stated, is that there exist these paths. How complicated it is to find these paths?
I think there are polynomial time algorithms to actually find the paths. At least for one of the two constructions, you can do it efficiently. That's not part of our proof, right? We just require existence, but I think in many cases there are, like these papers actually provide polynomial time algorithms to find the paths.
Thank you. Is there an intuition behind when the reverse direction protocols would exist?
Reverse direction means going from k EPR pairs to an n-qubit resource state?
Right.
Well, if k is less than n over 2, that shouldn't be possible. I guess even if k is equal to n over 2, that shouldn't be possible. Just consider the case where you have n over 2 EPR pairs and you want to go to GHC. I don't think LOCC can do that.
But in some cases, would it possible, and could we characterize those cases?
I never thought about it. It's an interesting question, but it's kind of orthogonal to what we studied, so I basically have no answer.
A bit of a naive question, but is there a way to attack this problem also through monogamy relations of entanglement?
The lower bound part?
Yeah.
It's an interesting approach. I think I tried to think about monogamy approach for the lower bounds, didn't prove anything. What we do is totally different, but monogamy also makes sense to study. Yeah, thanks.
Okay.
Hi, yeah, it's very interesting. So you kind of started motivating this by having the idea of these guys all having a big computation they want to do in collaboration, and
or anything on a quantum network would be a motivation.
So for me, like computation isn't usually something that happens in one step and then stops, right? So it's then natural to ask, you know, can I get these people to share to do this multiple times rather than just like?
Yeah, of course, the easy answer, like if you want them to be able to exchange 10 qubits, you give them 10 copies of the state, but that's probably suboptimal. You can certainly generalize the setting to the situation where you sort of specify, let's say, every specified pair of parties should end up with 10 EPR pairs rather than 1. And we haven't studied that, but it's a very natural generalization.
Thanks for the wonderful talk. So what happens if you have some faulty nodes? Say that at the end of the day, one node decides to stop collaborating?
I guess in that case, you only want the K parties to involve correct nodes, right? I don't think what we do still works, but it's not. It might be possible to fix it somehow. Actually, in the case of constructions 1 and 2, you know, if sort of the faulty node is sort of at the periphery of the network, these are sort of variants of expander graphs, so they will have a decent amount of redundancy in there. That might still work if there's 1 or 2 faulty nodes. Yeah. Again, something we haven't studied.
Hi, thanks for the wonderful talk. So to me, for k is equal to 1 case, it very much was connected to like reduced density matrices of a graph that you had GHD state, for example, because then if it has one body marginals maximally mixed, everybody can communicate with, one party can communicate with any arbitrary choice. So my question was, is there a deeper connection, let's say for n qubits, if you took a different graph state which had different marginals maximally mixed, let's say every 3 marginals maximally mixed, then wouldn't you be able to communicate between any 2 parties there?
I mean, it's just slightly ambiguous, right? I mean, you could either communicate between any pair or every pair. Which one do you mean?
So any 3, let's say,
Any
if
3
3 body marginals are maximally mixed, you don't have pairs, independent EPR pairs, but you have, let's say, 3 by 3 cluster state. And then you can still send an information.
But how many qubits per party is that?
1 qubit per party. But you have genuine multipartite entanglements, though. You don't have a network structure.
Again, I have to say, I haven't thought about it. I can't answer it off the top of my head. Sorry.
Thanks for this amazingly efficient Q&A. There have been many raised hands. I'm afraid I can't, give a chance to you all. There was one up here. Maybe, a final question. And please, as quick as the others.
It's a quick one. Hi, Ronald. Thanks. I was wondering, you're using some very nice graphs, which already been studied before. Have you also looked into hypergraphs and how they, like, using the hyper edges as GSE states?
Have not, no.
Okay,
I guess
thank you.
almost every question that I got, the answer was that I haven't thought about it. But I think this is a good thing, right? It means there's many ways to expand this research into other directions. So, yeah.